Oh, Carl, you haven't missed much as far as the alien question is concerned. Good evening, everyone. So welcome. And we have a problem tonight, right? Where are the aliens? And how would we recognize alien life if we saw it? We know where they are, right? I mean, they're up in space somewhere. They're out in the stars. I mean, we know where the space is. Thomas Carlyle helped us with that. We know where they are. And I suppose, the question is, what would they be? Something like that. I mean, you may have played that game. We'll talk about it a little bit later. The game of life, some sort of self-replicating, self-sustaining something. So, to put it in a context that most New Yorkers will understand, and I know we're not just talking to New Yorkers. Hello, planet Earth, to all of you out there and around the world. To find out where alien life is, what alien life is, to encounter alien life, there are four basic elements, basic questions that we need to grapple with here. The first one is, we've got to find, what is it? Planet. Well, no, we got to find planets, right? First, we got to find some planets, right? Right? That's the real estate question. Okay? So we need a real estate person, okay, to talk about where are the planets and, how many are there and just what is the basic sort of real estate lay of the land here. Second thing we need relates to your water question here. What do we need? We need to know what the planets are like. It's an interior decorator is what we need to deal with, what's on the planet, what chemistry is on the planet, is it rocky, is it gaseous, that sort of thing. So we need an interior designer, decorator, whatever. And of course, no life is possible, no real estate transaction is possible without a kitchen. So we need somebody who's good in the kitchen, who can deal with recipes, who understands the initial conditions of life from a microbiological, from a chemical standpoint here. And then, of course, you need somebody good with numbers, right, to make this all work. I mean, you really have to have the abstract notion of what is life, what are we really talking about here in the most abstract and stripped down cosmological way. So we need a real estate person, a decorator, someone good in the kitchen, and somebody good with numbers. Fortunately, we have those four people here in the house tonight. I want to remind you, before they come out, that you can ask questions of the panel at any point in the proceedings tonight. All you have to do is Twitter here in the house using the hashtag AliensWSF, Aliens World Science Festival, AliensWSF, and aliens is spelled A-L-I-E-N-S. Okay, just to help you out there. But let's begin. The real estate guy, an astronomer from Harvard, ladies and gentlemen, Dimitar Sasolov. Where are the planets? Yes, but what's on the planets? Our interior decorator, interior designer, she's an astronomer and a planetary scientist from MIT, Sarah Seeger. He actually is good in the kitchen, but he's also an investigator at the Howard Hughes Medical Institute, professor of genetics at Harvard Medical School, Jack Szostak. And oh, is he so good with numbers? Professor Paul Davies, physicist, astrobiologist at Arizona State University. So, first of all, welcome. Let's get started. How close are we to the encounter that Carl Sagan wished for? Paul, how close are we? Hours, days, weeks,
well, if
years?
we're talking about intelligent aliens, I suspect we're a very long way away from that. But if we're talking about microbes, for example, on Mars, could be any time.
Jack?
Again, if we're talking about very simple kinds of life, I think we'll understand more fairly soon about how life could get started, but you have to ask these guys about life out there.
Okay, out there. Sarah, what do you think?
Yeah,
How
we'll
close
give the
are we?
number of 10 years to 40 years, 10 years to 40 years, depending on how common life actually is.
Nice. And how will you detect that?
Well, we're
On
going
your
to...
like iPhone?
Well,
You'll get
we're
back
going
to
to talk later, but we're going
Yep.
to build large, complicated space telescopes.
Fantastic. And Dimitar, what do you think?
I think we'll have microbial life in the lab and then detected evidence on other planets before I retire. Soon.
Before you retire. All right.
I'm not planning to retire. But
You're not planning to retire. Right. Well, that gives you a hedge there. And just, it's a question I'm dying to ask. Does anyone up here believe that we've already encountered life that essentially came from somewhere else, but we just don't really know it yet? You think so? Well,
I think it's entirely
all right,
possible.
don't wait.
Nope.
We'll get to it. We'll get to it. I just wanted to know. All right, Dimitar, let's talk with you. It's a real estate question. Where are the planets? You're involved with the Kepler project, the Kepler telescope that's produced so many headlines. Tell me about Kepler. Tell me about the project and the Origins of Life Institute that you're involved with at Harvard.
The planets are everywhere in the galaxy. We have quite a few in our solar system, but not enough to answer the questions about life out there. Hopefully we'll discover it on one of our solar system bodies, but if it doesn't work, Sarah and I are already hedging on finding real estate out in the galaxy, and with the help of a few projects, we already know that it's very common. So they're around other stars. We know that there are billions of planets already. We know that number in our galaxy. And we are now after the best ones, just like in real estate.
Just
location,
like in real estate,
location,
yeah.
location.
Okay, so
that's
let's
what-
talk about location. What's the habitable zone, the sort of Fifth Avenue, Central Park West of...
So that's where you want to be, because as far as we know about life, and Jack will tell us more probably, and Paul later on, we need complex structures, and that requires temperatures which are not too hot or not too cold. So you have a solvent in which you can do this chemistry. That is a region away from the star, which is somewhere between the orbits of Venus and Mars, if you think about our solar system.
Depending
it depends
on
on
the
the
strength of the
star.
star, depending
Yes,
on
a
the star.
smaller star, it will closer for
Right.
the sun. So that's what we call the habitable zone.
How can you detect a body that far away with any precision, that close to a star? What is a strategy that Kepler uses?
Kepler uses a particular technique, which is called the transit method, and we'll probably talk a little bit more about that. But essentially, think of it as mini eclipses of the planets orbiting the host star, and those eclipses reveal the existence of a planet if you see them periodically. This is an example, what you see behind me, of one of the Kepler systems called Kepler 62, where the star is slightly smaller than the sun, but other than that is similar to the sun. And we already know that there are 5 planets that orbit that star. 3 of them are very close to the star, you see their orbits, and then 2 are further out with orbital periods of months, 6 to 9 months.
Right, but you're playing a game with me here, because Kepler does not see that gorgeous image, right?
Unfortunately, you're right.
Right. What
This
does
is
Kepler-
our
what does
very
Kepler
talented
see?
artist.
Yeah.
What Kepler saw in this case, it doesn't see it anymore. Unfortunately, it broke last May. But what we saw over a period of 4 years is dips in the brightness of the star, Kepler 62, which come periodically, and we realize very soon that they are not just 1 or 2 periods there, but 5. And each one of them comes at different depth, which corresponds to the size of the planet, because how much of the light of the star you obscure depends on your size. And this is essentially the technique. You don't see the star and the planet shadow
Right.
projected on it. What you see, you're measuring the brightness, and the brightness dips just slightly, ever so slightly, in fact, when the planet is very small, periodically. And that's why you need a telescope like Kepler, which is in space, which can monitor those stars without any interruption over a period of 4 years, and which is giving you an opportunity to see them come back again. Because if you see just once, You cannot determine the period. You don't know how far away this planet is from the star. And actually, you don't even know whether it's a planet in the
Right.
first place.
How do you distinguish between that and just the pulsations of a star?
That's right. So that's the big question. Pulsation of stars, you probably looked at the sun. Many of you probably have. They know that we have sunspots. Stars have spots. They look like this little spot there on the figure, which is the planet. How do you distinguish between the two? Well, that's why you need a very precise telescope like Kepler, which observes without any interruptions. So it has to come periodically back, and it has to retain its shape without any other changes in the brightness. Technically, that's how you know how
you don't want people to look directly at the sun, do you?
Don't look directly at the sun.
Very nice. Okay, so the exoplanet signature is this dipping of the brightness of the stars. And how far away are you typically observing?
Well, we wish that we're observing the nearest stars, but you already probably figured this out as an audience, that in order to be so fortunate to see those dips, the orbits of the planets have to be aligned just with our line of sight here on Earth. And that happens for about 1 in every 100 stars, even less than 1 in every 100 stars. So you have to, in order to catch enough of those planets, you have to observe 100,000, 200,000 stars. In order to accomplish this, the Kepler mission was designed to observe only one patch of the sky, the summer sky above our heads. Now, this time of the year, you can see the Kepler field. And only in that direction, we wanted to observe more than 100,000 stars in order to catch enough planets so that we can do the statistical estimate. Are these kind of planets like the Earth common? That means, however, a trade-off. You have to pay for these statistics. And what you pay is that all of these stars are relatively far away, about 500 to 2,000 light years away from us. So these are not the brightest stars that you see every night around on the sky. So we discovered those planets, but unfortunately they're very far away and difficult to follow up.
You'd have to go at like warp 10 to get there, something like that. Yeah.
You definitely shouldn't plan to retire soon.
Yeah, we couldn't get there by the time you retire, that's for
Right.
sure. All right, and tell me a little bit about Kepler 186F, which really made it into the headlines, and I have a really catchy name, I have to say.
186, yeah,
186F.
That's perfect.
I want to be from there.
Yes.
Yeah.
It's the right place.
Yeah.
I mean, listen, real estate is really good there. So,
Really?
Yes. Yeah. Expensive.
Condos on 186F.
What you see here is an artist's conception. Again, we have Kepler, brightness, dips. That's all we see. Another system with 5 planets. It seems good real estate comes in 5. What is special about this one is that for the first time we have a planet which is essentially the size of the Earth. You can see there Earth compared to this blank planet. We don't have an image to tell you what it's like. We only know its size and its orbital period and how far away it is from its star. So it is a planet like the size of the Earth, but it is also a planet which, with a period of 130 days, which is the year, the duration of the year on that planet, is in its star habitable zone, the green area that you see there compared to the solar system just below. Because the star is a smaller star, about half the size of the sun, the habitable zone, that is where the temperature is just right for liquid water on the surface of the planet and basically having a good time with your real estate. This planet is special. It's the first Earth-sized planet in a habitable zone of a star that we've detected so far. That's as much as we know, but it's a good first step.
And it's 5,000 light years away, so
no, not
ever
5,000.
go there to prove
not that
you're
bad.
wrong.
It's about 500 light years away.
Oh.
That's far.
So, God, I already feel crowded. Yeah. Okay, great. That's very exciting. And again, just remind us, you say there are billions of exoplanets in our galaxy.
Correct. So our galaxy, the Milky Way, that you all have seen if you ever left New York City, please do if you haven't, sometimes. the Milky Way galaxy has about 200 to 300 billion stars. We astronomers have spent 100 years on your behalf counting them, so now we know. Now we know, thanks to Kepler and some of the ground-based work that has been done on discovering these exoplanets, that the majority of these stars do have planets, and many of them have planetary systems, and a certain fraction of them have planets similar to the Earth in the habitable zone, which we already talked about.
Rocky, dense planets.
Yes, small size rocky dense planets in the habitable zone. That comes out to about anywhere between 1 to 5 billion such planets in our Milky Way galaxy. So that's the number we have currently.
All right. So then, Sarah, you have your work cut out for you. 5 billion potential candidates to determine what the chemical composition is, what the if there's water there, temperature, that sort of thing. What are the tools that you use to begin to ask those questions?
Before we get onto those tools, I just wanted to reiterate a really important point that Dimitar here has tried to make. It's about real estate again. And Kepler has gone out there to count, to do the census of how common are these planets. And the real estate thing that's important is we want the planets around stars that are very, very close to us. And just to hit the point home, the analogy we actually often use, it's really relevant for you, it's the Times Square analogy. Imagine for a moment you're in Times Square, and we've asked you to look at 200,000 stars or people at one time, but you're only in one line of sight. So you're looking in one direction. How many people do you see? 100 maybe? Maybe a few hundred? To see 200,000 people at once, like the Kepler Space Telescope did, you have to actually look quite far. You need your own telescope to look over to, I don't know, pick somewhere, New Jersey or even further.
Well, to use the Times Square analogy, you'd really get a distorted picture of New Yorkers if all you saw were the people standing around the naked cowboy in Times Square. But if you looked over in front of the ABC studio, you'd see different people.
Okay, right. So ultimately what we want, and we'll come to this later, so my first tool has to be a new type of space telescope that can look at the stars all around, not just stars in one direction very far away, but the ones that are really close by. And that is because we rely on photons. It's our currency. We need bright objects, so it's so hard for us to get the signal that we're trying to see. And so what we ultimately want to do, and I hope you were paying close attention to Dimitar's discussion, he said Earth
Her
size.
dissertation advisor, by the way.
Yeah, that was some time
A very
ago.
proud one, too.
Thanks. Right. He said Earth size, not Earth-like. So we actually try to be very careful because we have no idea. The blank picture of Kepler 186f is supposed to communicate to all of you that we have no idea what it's like. And so our next step is to find ones close by, and we want to be able to look at their atmospheres and tell more about the planet, the greenhouse gases in the atmosphere, to help us understand how hot or cold that planet really is.
But just to clarify, you need close-by planets because that gives you a strong enough signal to use the tools that you need to make the chemical questions and calculations.
So we want to be able to see the atmosphere and see the greenhouse gases in. And our real goal, actually, is to find signs of life on another planet by looking at the gases in the atmosphere. And we want to find gases that don't belong, that are in such huge quantities that with a lot of work and analysis in a probabilistic way, we can attribute them to life. And our best example here that we always give, we call it terracentric. It's sort of selfishness on a global scale, but we call it, it's oxygen. Our own planet has oxygen. We rely on oxygen, and it exists to 20% by volume of our atmosphere. But without life, that's plants and photosynthetic bacteria, we would have virtually no oxygen. And so we like to imagine that around one of those nearby stars, there is an intelligent alien civilization, although personally we've seen no evidence of them ever coming here. And that they're looking at us and they see oxygen, and that through a variety of logical steps, they infer, maybe not 100.0% sure, but they infer that there's life here on Earth. And so we're looking for gases that don't belong, and that's our goal.
And so oxygen is a marker for life. Without life processes or organic processes, there is no inorganic chemical phenomenon that would necessarily produce enough
There
oxygen.
actually are several ones. So we have this sort of game, if you will, in science, and someone says, well, it has to be oxygen, it's our best biosignature gas. And then other people will come by and say, well, no, here's the reason it won't be. And so we sort of go back and forth and try to figure out all the cases where we could have what we call a false positive, other ways it could be generated. And in the future, we'll need enough information to sort through all the situations.
All right, so describe the tool that you use to make some of these detections of what it is that's on these planets.
Well, the principle behind the tool is what we call spectroscopy. And if you can bring up the image, And what you see here is a prism, and the blue object is the star. It's supposed to be a star. And what it's trying to convey to you that we can take light and split it up into colors. And I hope that you've all seen a rainbow here. You don't need to leave New York City to see that, a rainbow. And you know what's so cool about the rainbow? It's sunlight split up by raindrops. But if you could look very closely and you had a way to look at it, you'd see that some colors, not whole colors, but some little slices of some colors are missing. You would see dark bands. And those actually are, if you can see in the image behind me at the very bottom, it's supposed to show the colors split up, and then at the bottom in that white patch, you're supposed to see dark lines. That's actually our own atmosphere is absorbing different molecules like oxygen and carbon dioxide and other gases are actually taking out, we would say, take out bites from the rainbow. They just absorb light, and that light is missing to some level.
So if you do the prism experiment, the Isaac Newton prism experiment in the vacuum of space, you get a standard, the same everywhere in the universe spectrum, right? But if you do it within a chemical medium of some kind or another, the signature is of the molecules based on what's absorbed.
Right, more or less. And this tool we call spectroscopy, and it's how we get most of our information in astronomy, looking at stars or galaxies or other planets. We see what molecules are there from spectroscopy, and so it's a standard tool.
Well, say we trained this tool on the Earth, okay? How easily could we determine what, say, a large group of human beings might be doing at a particular moment?
Well, let's back up a minute, because this tool is used on Earth all the time. We have, telescopes that look down on Earth, and they're measuring gases. We actually have deployed things all around Earth to measure, the changing gases in our atmosphere, or measuring emissions from other places. So it's a totally standard tool. But if we imagine like an alien civilization looking back at us, we'd say, what would they see? They would see gases like carbon dioxide. They would see water vapor very strongly, and that's indicative of surface liquid water. They would see oxygen and ozone. They'd see a whole bunch of things. But,
For a lot of Americans, soccer fans are alien. And I think we have a slide here which gives us a spectrographic sense of, okay, explain what's going on here.
What you see there is the World Cup soccer or football. And a device which you see on the on one side, which is a small telescope, trained with a similar prism, a way to see the fingerprints of a very important molecule to the organizers of the World Cup, which is called ethanol, and which you emit if you drink a lot of beer. So then, on the right-hand side, you see the result of that monitoring. You can see that a particular fan, there is a bright pixel there who is had quite a few of those. Probably.
And they got the best seats, too.
They have the best. Yeah, that's a very good seat there. So, in other words, we know how to do remote sensing very well. We've learned how to do that in the last 50 years. We use it all the time. And believe it or not, the remote sensing part of the big project of searching for alien life around other planets, around other stars, is the easy part. We actually know how to do that, and we're already doing it on some of those exoplanets. We know that it works.
We've done it in our own solar system.
We've done it in our solar system. So I just want to convey to you that this is a established technique which is very reliable. And
for instance, we know the composition of Jupiter, the gases in Jupiter. I want to say methane, but I'm not certain. But
it's a mixture of things, including
spectroscopy that told us about that.
But one interesting thing we should add, just so you don't think we know it all. Well, we like to think we know it all. But is when we have started to study exoplanets, not the small rocky ones, but we have about 5 exoplanets. They're typically very hot, very big Jupiters. They're extremely close to their star. So they're not what we're hoping to find in the future. But they actually have not turned out exactly as expected. So we have a theory that, we understand what elements and molecules will be in a planet of a given temperature. And it's actually not as simple as it might sound. So there's always a mystery. You're not always going to find what you expect.
Yeah, the technology is simple, but what you find with it baffles you. And we are certainly trying to understand. And that is actually the difficult part. We have the technology to look for life, but do we know what we're looking for is the big question.
Well, before we go to Jack on the sort of micro question there, can you give me an example, Sarah, of a spectrographic result that contains a lot of the mystery you're talking about, something that really baffled you, that had something you weren't expecting?
Yes. Okay. There's a planet. It's called GJ 1214b. I hope you
GJ. Okay.
I hope you appreciate that name also. And it was exciting for us because it was the first, we'll call it sub-Neptune planet. You know, we have different names for different types of planets. It's like Neptune, but much smaller and close to it's close to a very small star. Its temperature is about 500 Kelvin, so it's quite warm, but not super hot. And we all thought it would be just have huge water vapor signals. If you think about what elements are common in planets and what molecules could form, it has to basically be water vapor. So we used the Hubble Space Telescope, and we got data. And everyone around the world jumped on this planet and used whatever telescope they had access to, from something small to like the 8 and 10 meter telescopes. And the data was very noisy. And you know what? There's a sort of hint of water vapor if you looked at the data a certain way. And we've had so many of these moments in our history, like sort of together and apart. But you see something, you're so excited, you're sure it's something. It's like, wow, we think we found water, but it's what we would call a 2.8 sigma result. It's not sure, not certain. So what do? Great fuel for asking the Hubble Space Telescope for more time. Got a ton of time, expecting that signal would be now amplified with more data, and we would have a slam dunk. And it turns out it's like a straight line. There's no drop. You know, in all the colors, there's nothing missing. There's no water there. And there's what it means, we think, is that there's some clouds on this planet that are blanking out the atmosphere signal. Imagine when you're on a plane and you travel up through the clouds, and all of a sudden you're past the clouds, you can see nothing below you. It's as if there's a cloud all around the planet blocking the part of the atmosphere that would convey a signature. But there's many theories, too. People have come up with all sorts of ideas. So that's one case that is actually baffling us. And now we're, this summer, actually, our project, I think Dimitar is loosely involved in this, actually sponsored by the Templeton Foundation. We actually are going to do something in the laboratory where one of my colleagues at MIT, he actually has a cloud chamber, and so we're going to trying to sort through the options of what it could be. So that's one example.
Not to be annoying, but it's my understanding that the clouds are part of the atmosphere here on Earth. So you would be describing more of a Ziploc bag around the planet.
Right. Well, this other planet actually, it's quite warm. It's warm enough that we think it's too warm for water clouds. Our water clouds form as warm air rises and cools. So our understanding is that we can't. It's some other kind of haze, probably some smog type of effect.
And there's no chemical composition of the haze that you could determine.
Okay, so the thing is that molecules are really good. They rotate and vibrate, and they make strong signals. Haze particles are more complicated, and their signals tend to be much weaker if they exist at all. So that's the problem. They don't have a strong signature for us to see. But we're hoping that if we can make some progress in the lab, we could, in fact, identify what to look for in the future.
So haze is spectrographic noise, in a sense.
It's sort of like it just blanks it out. Yeah, it's actually, it's a problem. I mean, clouds are always a problem, right? It's a cloudy day, you wanted sun. So on these planets, it is baffling. And we have several other examples we could, at another time, go into more detail on.
So GJ 1214b, cloudy, with a chance of water vapor. Right.
It's a chance, but, it could also be something entirely different.
Okay, well, I'll remember that. All right, Jack, so let's talk about what it is we would be looking for on the micro level, on the molecular level, because we can add up all kinds of ingredients that we can see by spectrographic means, but the initial conditions for life are still a mystery.
That's right. So we have all these planets, right? We'd all like to think that there's life there, but we don't know really what the chances are that any one planet might give rise to life. So what we're trying to do is just go into the lab, do really simple experiments, and try to reconstruct a pathway, if not the pathway, by which life got started on our planet. And if we can show that there's a simple pathway and all the steps are easy, that would make it look like it was very easy for life to get started from simple chemistry. That would, I think, really encourage us all to look harder at exoplanets. Conversely, if we show that there are some really difficult steps, maybe some roadblocks, it could be that life is extremely rare.
We were talking backstage, some of the NYU students, that if there is no life except on Earth, then at the very least, unlike what Carlyle was saying, that space is just a huge waste, that we here on Earth would have huge abandonment issues to deal with for the rest of civilization. So there is a planet that we know has life. It's near to the sun, but yet it is almost impossible to find the conditions on this planet pre-life. to make a chemical, a calculation of what were those moments when pre-life became life.
It's ironic that I think soon we'll know more about the atmospheres around planets elsewhere in the galaxy than about the early atmosphere of our planet. And that, knowing what the conditions were early on here, would be really helpful for us. So lacking that, we just really basically have to go back to fundamental physics and chemistry and see what the possibilities are and try to figure out what kind of environments that are reasonable on a young planet, would foster the emergence of cells that could evolve into more complicated forms of life.
So, and that would have to have taken place on Earth about 4 billion years ago, right? Something like that?
Yeah, plus or minus 500 million.
500 million, right. I mean, I know there was no Times Square back then, for instance. What do we think the atmosphere looked like? What do we think the sun's rays looked like? What do we think the chemical composition of the surface of the Earth was like? Do we have any stabs at that?
Well, there's a lot of different opinions. Actually, Dimitar and many of his students have been modeling early planetary development. Back when the Miller-Urey experiment was done 60 years ago, people thought the early atmosphere would be very reducing, which would make it very easy to generate lots of organic chemicals. Then the pendulum kind of swung the other way for various reasons. People thought the atmosphere might have been more oxidizing. I think it's come back a little bit now, but now we're also thinking more about local environments, ways in which events like impacts could perturb atmospheric chemistry, maybe for significant periods of time. So, the planet's not homogeneous. Right? There are lots of different environments. There could be different chemistry going on in different places at different times.
What chemistry do you think is a necessary or sufficient condition for the production of life? I was told in high school biology back in the 70s that life must have begun in tidal pools, near the sea. But
I think maybe you had a pretty good teacher back then.
Really?
I still kind of like ideas like that. Maybe small pools, ponds, lakes on land. So I don't like the idea that life started in the ocean. I mean, the ocean's too big, everything's too dilute. When you're on land and you can have evaporation, right? Chemicals can get concentrated. They can react with each other. You can have more interesting chemistry going on. Environments like when you have an impact, make a crater, or if you have a volcanic environment, you can have hydrothermal circulation, so you can have temperature fluctuations as well as chemical variations. So those are the kinds of interesting, complicated environments we like to think about.
We know that DNA is the molecule that forms the basis of life on this planet. What is the candidate molecule or class of molecules which might be the the pre-step, the last non-life step before we get to life?
So all of modern life, of course, uses DNA, as you said, but basically to store information and to pass it on to the next generation. At the other end, all life on the planet uses proteins to do almost all of its chemical reactions and to build interesting structures. And then in the middle, and doing lots of different jobs, is a molecule called RNA, which is a close chemical relative of DNA. And I think the best theory going now is that life started using RNA as both its genetic information store, but RNA can also fold up and make enzyme-like shapes and catalyze reactions. So it can kind of do everything not so well, but maybe that's a way to start with just one interesting kind of molecule. So behind me you see an RNA molecule. This is an animation that was made by Janet Iwasa in my lab. It shows an RNA molecule floating around in a rich chemical environment with nucleotides that are kind of clicking into place by base pairing and building up a copy. So one of the problems is how you replicate useful information. And trying to find a simple chemical way of doing that replication is actually one of the things we're focusing on in the lab now.
Can RNA do that now? Can you put RNA that is clearly lifeless in some sort of environment that then it becomes some sort of sustaining something or other?
So we can't quite do that. We can't really replicate RNA yet without enzymes. So there's a whole long list of problems that need to be solved. And in fact, I wrote an article a couple of years ago called The Eightfold Path to RNA Replication, because there are 8 big problems, and if we solve them all, we'd be in nirvana. And I think
7 days creation, 8 problems. Yeah.
Slight problem there, slight issue.
Bible's got you beat, I guess.
Yeah. I think we're doing pretty well. I think they're all going to be solved within a few years.
What are the mechanical issues of creating structures that would do what cells do? There's a real architecture question on the molecular level.
Absolutely. So, of course, all cells have an edge, a boundary, a cell membrane. And that cell membrane is made of fatty molecules, lipids. And they have a very beautiful property, which is these molecules, which can be extremely simple, will just spontaneously self-assemble into sheets and then close up so that they encapsulate some volume of liquid. So the picture that you see behind me is, just a drawing, an illustration of a cell membrane, a very primitive cell membrane, sort of sliced open, and so inside you can see a few replicating RNA molecules. This is the kind of really simple cell. So we call it sometimes a protocell. It's much simpler than any living thing on the planet now, but maybe the first cells were something like this, something that could self-assemble given the right collection of molecules.
Can chemicals create membranes like that?
So we often work with simple fatty acids. Basically, they're soap, essentially. You take these molecules and shake them up in water, and they make structures like that spontaneously. And this video, if it's running, shows what would happen when if you add more food, more fatty acids, these things grow spontaneously. I mean, it looks very lifelike.
So these are like little bubbles, sort of.
They're like little soap bubbles, except in water. And if you add more fatty acid molecules, they'll absorb them, and they'll grow into these long filaments. And then making those divide is very easy because the filaments are very delicate. And the little video that's playing now shows one way that a filament can divide spontaneously into lots of daughter cells. So just very simple molecules in simple physical systems give you phenomena that are just remarkably lifelike.
And how close do you think we might be to actually taking some of those lab-based mechanical cellular creatures and filling them with enough RNA to cross this boundary here?
Well, so we've done that, and we just published last year a result that I think for us was kind of a milestone. We could start to copy RNA sequences inside model protocells like the ones that you saw. Now, if we could just go a few more steps and get that RNA to completely be copied and go through cycles of replication at the same time that the vesicles are growing and dividing, then I think we would have a cell-like system. It would be something that could start spontaneously evolving, which is what we really want to see.
So you've basically created soap-like substances that are nearly alive.
They're the boundary of the cell, but
Right.
But to really have life, to be able to evolve, you need an information system. So that's where the RNA comes in.
If you come over to my house, though, there's soap in our bathroom that is alive. I have 5 kids. I mean, I guarantee you. Well, all right, so let's say the aliens land. The aliens have landed, and there is an encounter, and, the Pentagon or somebody who is responsible for all of this determines that, in fact, something has happened, and, we need to call somebody to tell them or what to do next, because assuming we don't want to, immediately call out the Pentagon to confront the alien life forms, who do we call it's you, isn't it?
I'm your man, yes,
Yeah.
yes.
I mean, that is literally true.
Well, if the protocol works as intended, of course. But
What is this protocol?
well, I chair a curious body called the SETI Post-Detection Task Group. SETI stands for Search for Extraterrestrial Intelligence. So now we're leaping from little blobs to little green men.
Post-detection.
Right. And so the job of this task group is to deliberate on what we should do next in the event that we get incontrovertible evidence that we are not alone. It hasn't happened yet, but I often say at dinner parties, it goes down well, that if E.T. calls on my watch, I should be the first to know.
But does that mean, does that literally mean that there's some sort of Arizona area code that if you call it, they pick up, hi, SETI Post-Detection Task Force?
Right.
There is?
Well, not quite like that.
Okay.
There is this group of people. It's international. The big problem is it doesn't have a budget. So,
that is a problem.
So we can't get together that often, but from time to time, at least a group of us do. And you see, it's more than we're sitting around waiting for the big day. We're thinking about, well, supposing it happened, and it may not be we pick up a message from an alien civilization. It may be that we detect some weird thing out there that on closer inspection seems that could have no natural explanation. Then what is going to be the impact on society, on our science, on our religion, on our technology? What next? And so it just pays to be forewarned, or to be forewarned is to be forearmed. So we are sort of trying to think about the impact, should this occur. And as I say, it may not be a signal from the aliens. It could be that we just stumble across something that is going to convince us we're not alone.
You know, I want to pursue this just a tiny bit more. And it occurs to me that if the world actually is thinking along these lines, you'd kind of want the president to have, one of those officers with a briefcase. And, I guess there's the nuclear launch codes in there. That's the big joke. But you'd also have, your phone number would be in there, too, in case.
I like to think so.
Yeah.
But it turns out...
Are they supposed to call you?
It turns out, that basically politicians, and right the way up to the United Nations, has almost no interest in the subject of SETI. And so this is driven by scientists and well-wishers. So this task group contains some media people, and a priest, and a couple of science fiction writers.
Buzz Aldrin, probably?
Not yet. No,
not yet.
He's invited. And it's an advisory body only. So we can't... So supposing you are the one that makes the big discovery, you're sitting at a radio telescope, there's nothing I can do to then say, right, we're taking over now. It's all under control. Don't tell anybody. So we can't do that. We can merely advise it would be sensible to do this or to not do that. But the problem is that a discovery like that, which would be unique in the history of science, it's almost impossible to predict, particularly in these days of social media, how it would actually pan out on the day. And you can imagine that everybody might want to do the right thing, but somebody's only got to text their girlfriend or something like that, and it's out there, and then there's a media frenzy, and then the astronomers can't even work to study the problem they're dealing with because they're besieged by the media.
Well, there is that interesting trade-off. I mean, you can't be too secretive, and I guess Donald Rumsfeld already tried the "I'm in control here," or Alexander Haig, or someone like that. Yeah. But
I tell you what, we don't want. You see, we don't want any proverbial Tom, Dick, or Harry commandeering a radio telescope, pointing it at where the message comes from, if that's the way we get the evidence, and beaming their own personal homespun wisdom on behalf of planet Earth. So I think if there is going to be a response, it should
keep
be...
your cat pictures on your hard drive, okay? All right. It just occurs to me, anybody, has it ever occurred to any of you out there to pick up the phone and call the SETI Post-Detection Task Force? With that one hand here.
Hi, that's very good.
Please do not give him a microphone. Okay, thank you very much. All right, so let's talk. Forget chemistry, forget spectroscopy, forget exoplanets. The conditions for life are more of a philosophical, cosmological matter. It's a question of what is life independent of the molecules.
Right. I'm pleased you've raised that because we've been skirting around the business of a necessary versus a sufficient condition. Well, you actually raised that. And however many Earth-like planets you've got out there, all you can say is that these are potential, these are habitable planets. That doesn't mean they're inhabited. And the only way in which a habitable planet becomes inhabited with life is if the transition from non-life to life occurs. And as Jack was saying, we have no idea whether this is something that is almost inevitable given Earth-like conditions, or if it involves some bizarre, fluky chemistry, a long string of very improbable reactions. We have no idea. And so the error bars on this issue about the probability of life emerging on a planet, if it's out there, are enormous. And so what we would like to do is reduce those error bars. And one way of doing that, well, Jack has already said, we can try to recreate the first steps in the lab, but there may be many steps, there may be 1 million steps up to even the simplest living thing. So it could be a very long project. And the other way is to try to get a theoretical handle on it, and that's the work I'm involved in with my colleague Sarah Walker, largely by looking at toy computational models. And Jack very conveniently introduced the I word. You see, if you ask a physicist or a chemist what is life, you'll be given a story in terms of molecules and forces and thermodynamics and activation energy. You ask a biologist what is life, and you'll be given an explanation in terms of things like coded instructions and signals and translation and transcription. In other words, information speak. And so the distinctive thing about life is it is not necessarily what it's made of, but the way it manipulates processes, manages and organizes information. And it does that in a very distinctive way. And so we think that really the origin of life involves two origins. One is the hardware, and the other is the software, the informational aspect. Now, for about 100 years, the field has been dominated by chemists trying to cook up the hardware in the kitchen, as you were saying earlier. We're trying to figure out how did the software get cooked up, or how did it come into existence. And that's a field very much in its infancy, because the whole idea of information, it's a slippery concept, and there are many different definitions. The one thing we do know, though, is if you look at existing living organisms, they are processing information in many ways, both analog and digital, in complex patterns, but in ways that can be quantified and studied in toy computational models. So that's the way we're going at it, to try to get at that software.
What's an example of that? I think I showed
Well, you showed the game of life,
yeah.
which is really just a cartoon of life. But what it shows is that some very simple rules. Now, a lot of people here will have played this game. It was invented by the mathematician John Conway, and it's an example of a two-dimensional cellular automaton. And it just means that you have filled pixels and empty pixels, and there's rules about, with each step, whether you, as you update the system, whether the filled pixels stay filled or become empty and so on. And what you discover is, for some of these rules, just continually repeating this update gives rise to what look like organized complex structures. They're not that organized. You know, this is,
well, in this case, this is just about 12 iterations repeated over and over again.
Yeah, lifelike. And so that's just one way in which you can get a handle on this. Now, we want to go beyond just playing those simple games and ask if the information, where is the information flowing in this system? And there it's just really flowing in the little blobs that are moving around. But we know in real living systems, the information can be captured by collective modes, collective degrees of freedom in the global structure. Biologists talk about this all the time, the microenvironment of the cells, signaling going down to the genetic level and upregulating genes. So this idea of the flow of information from the top down is part of biology. In physics and chemistry, we're more used to bottom up. So we're trying to adapt these cellular automata to incorporate this top-down approach.
So before we move on, it occurs to me, how much do you rely on what each of you are doing to ask questions, to think about experiments, to think about projects to do? Are these four voices very, very independent, and I would never see you in the same room except for the World Science Festival? Or are you thinking about these things? Do you really think on a cosmological level as you're looking for exoplanets? Do you think about what Jack is doing, Sarah? Anyone?
I do.
We actually work very closely together with the people who still work on this bigger question. Quite few.
The beauty
and
of
we
this...
know each other very well, and we work together. So we've been together on numerous occasions.
Yeah, I mean,
we have projects together.
Right, I'll say it's sort of
we
a yes
collaborate.
and a no. It's a no in that, like in our daily TDM, we're sort of having to focus on what we're doing. But if there's a larger question that we need help with, we definitely will approach each other.
Do you have, like, the same seats at Fenway? Red Sox games? I mean, you're out in Arizona. It's kind of you're at a disadvantage.
But not really, because...
The Diamondbacks suck this year.
Never watch them.
Yeah.
The beauty of this subject that's called astrobiology, which sort of encompasses all of this, is it brings together chemists and physicists and astronomers and mathematicians and computer scientists, mixes them all together. I think it's been a wonderful exercise for me over the last 20 years getting involved in this, to rub shoulders with scientists from these other disciplines, because we need something of everything that has been represented here this evening, and other things besides. So this is truly multidisciplinary.
Jack?
Well, I was just going to say that it took a while. It was several years of us sort of talking and learning what each other were doing. But Dimitar and I are starting collaborations on a couple of different projects, and we're both really interested in, the particular environments and some particular aspects of the chemistry that can be tested in the lab. So it's been really, really fun to talk to people in different fields and find some common ground.
And
we work with people who have labs who work with microbiology, who collect life from extreme environments, and we do things to them and see what rates of output they'll produce of the gas that they're making. So there's a lot of crosstalk in the field.
So we definitely need each other in this process, because we rely on our biologists and chemists colleagues to design what is the next generation of remote sensing instruments. And they are motivated by what we are finding to do the work they do. So there is not only a synergy in the final goal, but also an interleaving in what we do on a daily basis.
And Dimitar, you scared the hell out of me earlier. You just told me that there was a conference where you were all invited to the Vatican to talk about this. And I immediately thought to myself, so they took you to the Galileo room?
Were we all there? Were you there?
No.
Okay.
Well, but you were telling me that a bunch of astrobiologists were invited to the Vatican, and it wasn't like they asked you to recant or... There was no execution or anything?
Let me talk about that. I'll mention.
Yeah.
It was actually, I will say it remains to this day. I'm not sure if it remains for those rest of you. One of the most interesting meetings I've ever attended. We stayed inside the Vatican itself. And if you've ever been there, if you start to approach, it's those Swiss guards are all really well dressed. But we had a special key. It was literally like this big, the keychain on the key, because we stayed inside the Vatican where the cardinals stay when they choose the new pope. And it's, they're really plain. It has to be sort of plain, but this was the most fancy plane you've ever seen. And we had our meeting in the place where Pope Pius IV's old residence. And actually, the room where we met, it was so civilized because you had to press a button for your microphone, but only 2 buttons would work at once. So any other party couldn't jump in and start arguing, as we usually do with each other. The food was tremendous. They fed us 2 meals a day, which were unbelievable. Many courses. Each course had a different type of wine. But actually, you want to know what was the real reason we were there. And I'm really glad that this part came up, because I have a special word that I use for it. And this is a word I came up with a friend one time, quite some time ago. And we call it the awakening. What we mean by this is that the world is starting to realize, and the Vatican realized that actually, this meeting I think was in 2009, so it was well before most of the rest of the world, that we're getting close. We're getting closer and closer to possibly finding signs of life. Now, they never told us the real reason they gathered 30 of us there.
It's obvious.
No, it is.
The great
actually,
plane, the fabulous food. They say, forget science.
Well, the thing is,
give me the Bible and more of that fettuccine.
They were extremely sensitive to, we weren't there to talk about religion, although, of course, it came up when we were on our own. But, they really want to know, what is the chance? It's really, they have to figure out what it means when we find life elsewhere. That's for them to find out. But they had us there to sort of figure out whether it was going to happen anytime soon or whether they should worry about it.
Is it possible that, what we've been describing here, that it's a very difficult task to get the initial conditions for life, to figure out exactly where in the universe it might happen, and to detect it as it happens, or close to as it's happened. Is it possible that we could have cheated? You raised your hand earlier that
Right.
it's possible that life forms from another place have already encountered Earth, and that in some sense we might be the product of it.
Right, so there's a very natural mechanism for the transport of microorganisms from one planet to another that are near neighbors, and Earth and Mars are the obvious examples, that these planets from time to time take a hit from a comet or an asteroid with enough force to blast rocks around the solar system. And we now know that microbes can live inside rocks, and cocooned in a rock could survive the harsh conditions of outer space for certainly thousands, maybe millions of years, long enough to make it to the other planet. And although it's a sort of hairy ride, nevertheless, some of them are going to survive and be viable. So I think once you get life on either Earth or Mars, you're going to very soon get it on the other one. And we know Mars was warm and wet 3.5 billion years ago, when we know there was life on Earth. So this traffic of rocks back and forth between these two planets almost inevitably means there would be an intermingling. Now, what we'd really like to know is not, is there life on Mars or was there life on Mars? We might go to Mars, we might spend a lot of money, drill down, find life, and it's good old Earth life. It's the same as us, which either means it got there from here or we got here from there, that we're all descended from Martians. Entirely likely, in my view, that it could be that scenario. What we really like is a second sample of life. We'd like to know, we'd like to answer the question that Jack raised, just how likely is it that life will form from non-life? At the moment, we've only got one sample. And so it's impossible to say on the basis of that whether it's a bizarre freak event, unique in the observable universe, or whether it's something that will happen on almost any Earth-like planet. We don't know. But just one other microbe that is not Earth-like. It's got to be sufficiently biochemically different that it cannot have a common origin. So what we'd really like is to find that. We'd like to go to Mars, find a little Martian, and look at it and study it and say there's no way that that could be related to life on Earth. For example, it might be the mirror image. The molecules might be all around the other way. That would be...
What does that mean?
Pretty well. Pretty much all of your amino acids are left-handed and your sugars are right-handed, and that all known life on Earth shares this common chirality, as we call it. So in a mirror...
But there's no particular reason why it couldn't be
the laws
left-handed.
of physics don't care left over right. So if you do the whole great experiment again, you can have it round the other way next time. So if you found a planet with life on it that had reverse chirality, even if it's the same basic building blocks, then it would be very hard to see how there could be a common origin.
We're getting a question on that particular point. Atif Syed from Edinburgh, in Scotland, asks, in terms of chemistry, what similarities would we be expected to see if we found alien life? What are the other sort of chemical substrates that might work, Jack?
Yeah, well, that's a fantastic question. We know that in terms of the membranes, you can make membranes out of lots of different molecules. As long as they have one part that is sort of oil-loving and one part that likes to be in the water, you'll make membranes. So it gets more interesting when you think about the nucleic acids, DNA, RNA. What else could work? And through the efforts of synthetic chemists, we now know there's a whole large family of related molecules that apparently could work perfectly well as genetic molecules. The only catch is, most of them at least, it's not obvious how they could ever be made on the early Earth. But there are a couple of alternatives. There's one called TNA that people are excited about studying. And so if we found a form of life that used a similar but chemically distinct nucleic acid, that would be pretty exciting.
Are there places on Earth where we could test some of the hypotheses about life existing on Mars, places that are as rugged?
Yeah, there are Mars analogues. The closest is the Atacama Desert. I think we've got a picture here somewhere. Visited there some years ago. And it looked at first as though nothing could live. This is the dry core of the Atacama. It looked that because we all think that life, at least as we know it, requires liquid water. There is no liquid water. It never rains there. It's very, very dry in that inner core. And it seemed impossible that anything at all could live there.
And it's salt. It's a highly salt environment.
It turns out that even there are organisms that eke out a living in these pillars of salt. This is a evaporite lake, so these are salt structures, and inside the salt, there's a phenomenon that I learned when I was about 15 called deliquescence, you see, and you think, has anybody heard of that? I don't know if people learn this stuff these days. Deliquescence. And what it means is, on a damp day, you can't shake the salt out of the container because it absorbs water vapor from the air and gets sort of sticky. So salt has that possibility that you can suck in water vapor and retain it in the matrix of the salt. And these little critters live inside this salt, and they've got just enough water molecules to do their stuff.
They get it from the salt.
They get it from the salt, but they need photons because they photosynthesize. So when the sun comes up, they think, aha, we got the photons, but oh no, it's going to evaporate the water out. And so there's a sort of sweet spot. It lasts for about an hour when they can, have a party, and then they have to go dormant until the next time. And so even there, and maybe on Mars, there's something like that.
Join the party, Jack.
Well, I'd like to make a point about this. There are all kinds of incredible extreme environments like that on Earth that are populated with all kinds of weird living organisms. But that doesn't mean that life could get started in any place like that, right? The environments where life could get started are probably much, much more restricted. And then once you have Darwinian evolution going, of course, you can start to adapt to different environments and sort of gradually explore and colonize the whole planet. But your question in terms of whether an exoplanet might have life depends on, does it have those environments where life could actually get started?
And we don't know what those environments were. That's the problem.
Well, I think from the chemistry that's being done in many different labs, we are starting to get at least close to being able to deduce some of the requirements in the environment.
And you made the point that you don't want it to be too dilute, so two-dimensional catalytic surfaces, little pores in rocks and things like that help.
And I think you need things like quick temperature changes, right? If you're going to replicate RNA or DNA, you need to get the strands apart, which means you need to heat it up. Right. But you don't want to cook it all day.
So does that mean you want rotation, Dimitar?
Yes, and that's a good example of where we actually need that research done before we deploy the large telescopes and get data on those remote sensing spectroscopic features from distant planets, because this constraint in those conditions allows us, the astronomers, to tell whether the signatures we are detecting there could be due to life or could be due to the geochemistry of those distant planets.
That's fascinating. Let's talk about that in just a second. Why don't I give you this question that I think relates to what we're talking about right now. Joshua Phelps says, if we look for life on a planet located where water can be found, are we ignoring life that isn't water or carbon-based? Obviously we are. What could be not carbon-based? There's silicon talked about from time to time.
Yeah, the chemistry of carbon is just so much richer than anything else, and it just seems so much easier to get started with carbon and, say, nitrogen and oxygen and hydrogen.
But let me take it from the observational perspective, because one thing that the astronomers, the true observers, will say, they won't listen to any of this theory because they say, well, we're going to look anyway. And so we won't know if the life is silicon or carbon-based or what have you. We can certainly speculate. We're going to infer that life is there, but we won't be able to see anything else about the life. Now, I'd like to address that water question because it comes out quite a lot. And there are people who believe that life just needs a liquid. Any liquid, many liquids would be suitable. But again, in the observational sense, water is still our best bet. We could actually evaluate which planet, at different distances from the star, assuming that rocky planets are heated by their star from the outside, have different liquids. And actually water is extremely abundant, and there's quite a range where we think water can be liquid. Other things like carbon dioxide, a very narrow range where it can be liquid. We have to go quite far out till we get to the next liquid. It would be like as far as Saturn is from our sun. Saturn has a moon Titan that has liquid methane and ethane lakes. But that's so far from the star, the tools we have at hand or that we're developing to look for small planets, we couldn't see those. They'd be too cold and dim. So in a sense, we're not necessarily limited to water. It's more of an observational problem for us.
But I'm not hearing a message from you that we're, creating a planet of carbonists who would be intolerant of non-carbon-based life forms. Then we get into a whole other problem that we would be repeating again and again. Dimitar, what do you think?
I think we have to be practical about it, and carbon is a very good base for the basic structures. And then you have all the possible alternatives, which Jack brought about. And so if we want to be practical about it, we're looking for potentially habitable planets out there where water and the combination of carbon chemistry is the most generally available medium for us to search for. And so the search on practical levels have to go that way, at least in the beginning.
Sixth grader from Pennsylvania. What would happen if bacteria from Earth got on another planet, and what are we doing to prevent something like that from happening? Anybody?
NASA has a planetary protection officer, and I was interested in that job because I thought, wouldn't it be cool to chair the SETI Post-Detection Committee and be the planetary protection officer? The Earth is safe in my hands. I'd have it.
Conflict of
sewn
interest,
up,
though.
But no, I'm not a U.S. citizen, so they turned me down.
Only a U.S. citizen could be a planetary protection officer?
Right.
Boy, I did not read the UN Charter very carefully, did I?
That's right. It's basically a NASA appointment, you see.
I see.
And the job of this individual is to both prevent forward contamination, that is, we shouldn't send Earth bugs, say, to Mars, and back contamination, we shouldn't bring back in a sample return mission any soil that would release a killer plague to wipe us all out. This has manifestly failed, this endeavor, because we have contaminated Mars many times with our sloppy sterilization techniques with the spacecraft that have been sent there.
Here's a great question, classic sort of World Science Festival question here. JC from Rhode Island asks, could you elaborate on the recent controversy about the Martian meteorite Yamato 000593 and the evidence of microbial life on ancient Mars? Anybody? JC wins the Lexus. He stumped the panel.
There are a lot of things that have fooled people over time. Structures that come from chemical and physical processes that kind of look like or are reminiscent of cells, ancient fossils people have been fooled by, structures on meteorites people have been fooled by. You have to be super careful and have lots of lines of evidence if you want to make a conclusion about something so extraordinary as, this is coming from life. And I think almost nobody believes that.
There's one thing I'd like to say, because he's a friend of mine. Gil Levin developed the labeled release experiment that went to Mars on the 2 Viking missions in the 1970s. The last time NASA ever did a biology experiment on the red planet. A lot of people don't know that. And that experiment gave a positive result. That is to say, he designed it to detect the sort of life that you would detect here on Earth. It was positive in both sites. When he heated the sample, it was negative. So it did exactly what it was designed to do, but the conclusion was still that this did not constitute...
Well, it was a carbon dioxide detector, right?
Yes. It gave off a carbon-based gas, yeah. So it consisted of pouring a radioactively labeled nutrient medium onto some Mars soil and seeing if it fizzed, and it did fizz. And there could be all sorts of complicated chemical reasons why it fizzed.
We understand now what happened.
Right? Well, I think we understand because we're the perchlorates and so on.
Exactly.
So, but it's worth remembering that experiment was done, and it's consistent with life, but it does not prove it. And that shows the difficulty in this whole game, because you have to have a criterion. What are you going to look for? And that's what the subtitle is here. And I notice it says, will we know it when we see it, not would we know it if we saw it. But, if you're going to do a test and you're going to design something, and then you get the best brains, they design something, you spend a lot of money, and then the test is positive, and they say, oh, I can't be right.
Well, that raises the question that you started to talk about, Dimitar, a moment ago, that we have tools that are coming online very soon that will be able to detect signals much more much weaker signals than we've been able to test up till now. But unless we're asking the right questions, and some of those are your responsibility, it may all be for naught. What's coming online? What kinds of tools are coming online?
Oh, the first thing that is coming online is now that we know that, statistically speaking, we have a large common occurrence of this kind of planets, we want to discover them not just farther away, where Kepler does, but the closest possible systems to us. And that is a project that is led by MIT and is in collaboration with Harvard and NASA. It's the NASA TESS space mission, which is a follow-up on the Kepler space mission, which is going to do a very similar survey to that of Kepler, in other words, using the transit method to discover planets, except that now it's going to survey the entire sky, and predominantly for those stars and planets which are much closer to us, significantly closer to us. And then that will be followed up by the successor to the Hubble Space Telescope, the Webb Telescope.
The JWST, it's called, right?
That's right, the James Webb Telescope, which is going to allow us to study those.
There's an animation here which shows
Yeah.
you it's one of the more complicated things
going
that
to
we...
So explain
follow you
what we're
through
seeing
that.
Well,
here.
it's the James Webb Space Telescope. It's an animation of a mirror. The mirror is effectively 6.5 meters in diameter. Hubble is 2.4 meters in diameter. And
That
it's
yellow
showing
thing
you-
is the mirror, right?
The yellow thing is the mirror. And what it's showing you is the thing has to deploy. It folds up so that we can fit it into a launch vehicle. And it goes into space far from Earth to a place called the Lagrange point. And you can see the part at the bottom is actually a tennis court-sized solar shield, essentially. And it's several layers of all very special woven pattern. But each layer is different from the next one. It's controlling the heat so it doesn't go through each layer and get re-emitted and heat the telescope.
That's the power source.
No.
It's just blocking the sun.
Oh, it's
so it
blocking
doesn't heat
the-
the
it's a
telescope.
shield,
Yeah,
right.
that's right. And so there you see the telescope. You'll see that the mirror now, parts of it have to unfold. And the sequence takes place over a couple of weeks.
Oh, man.
There you go.
And everything has to work just perfectly.
You know, everything
there.
has to work, and people do worry, but the one thing that hopefully reassures you is all the mechanisms that have to spring open and unfold. Those types of things have been done literally thousands of times, thousands of mechanisms like that.
And that's going to be like Hubble. That's going to be an optical and
infrared.
infrared.
And in
More
fact,
so
it's
than Hubble.
cryogenically cooled, so it goes into the infrared quite a bit as compared to Hubble.
All right, and then there's something else that we can talk about here that's actually right on stage. You'll notice over here this art object over here next to Paul is not actually something that we purchased at IKEA just for the festival. It's actually part of a very sophisticated follow-on to these two devices that we were just talking about. Explain what this is.
Yeah, I'll explain it, but before we get to that, all we've been talking about so far is the transit method, planets that go in front of their star as seen from the telescope. And as Dimitar mentioned, it requires a very special alignment. We think planets have orbits that are all randomly aligned with respect to us and their star. And so when we exhaust that kind of technique, we have to turn to other techniques. And so the next technique involves this actual so-called artwork. I think it's actually very beautiful if you take a close look at it. And what this technique is, we call it direct imaging. The goal is to block out the starlight so we can see the planet directly. And this is part of a larger thing, which we'll get to in a minute. But an analogy, it's as if if you turn up and look at the lights, they're so bright, but we want to just block out that light so we can see a faint object right beside the bright light. Essentially, a planet like our Earth, if it were tens of light years away, it's about as faint as the faintest galaxies ever observed by the Hubble Space Telescope. So in principle, we know how to observe faint objects. But how to observe a very faint object next to a 10 billion times brighter object is something that we have been working on how to do. And just
So it's like the windshield thing in your car.
what do you mean?
You know,
The
you
sun-
pull it
Oh.
down, the sun shield.
It's like the sun shield, except it would have to block the light in such a perfect pattern to 10 decimal places. So yes, it is that kind of basic principle. And so if you can bring up the animation, we have an animation to explain this concept. And you'll see we call this a petal. It's part of here you see a telescope and another thing called the star shade would launch together. And the star shade is a specially shaped screen. The petals would unfurl from their stowed position. A central truss will expand, and these petals will snap into place. And it's this very specially shaped screen that would have to move away from that telescope to literally tens of thousands of kilometers. And that screen itself is about 30 meters, tens of meters in diameter. And this is an artist's conception showing you how it would work, blocking out that huge glare from the star to reveal the planets beside it. And you see here, we call it flower power. It's a very, specially shaped petal. And please don't go on to the next video yet, because I want to explain this a bit further. This is one petal. That's how big it is. This is one petal out of that whole picture.
Now,
and I just want to explain why it's this very special shape.
But let me just ask one question about the mechanism of how you do that. So does that petal, the flower power thing, does a computer calculate, all right, we want to look at this star, so therefore it moves to a particular location?
Right. It has to, the telescope and the star shade have to be aligned very carefully, and when they're done, either the telescope or the star shade moves across the sky to the next star.
Is it the same distance for each star that it wants to look at, or?
More or less, yes, because the
okay.
stars are so far away. However, we do, in some cases, want to move that closer or further to the star, just depending on which wavelength we want to look at. But you might find this interesting, how much time that right now I'm chairing a team sponsored by NASA to study this concept, how much time we spend arguing over the observational sequence. And we're actually going, our next meeting is going to be in Chicago, actually, at a planetarium, and we're going to use the sky to show where the exclusion, where the sun would be and where the Earth is, it's too bright, and where our stars would be. And we're going to kind of play a game where we roll a 10-sided dice. Because we think about 1 in 10 stars would have an Earth. And we're going to say, okay, we're looking at this particular star. We see a blob. We call it the blob. Maybe a planet around it. But how do we know what it is? Is it a mini Neptune? Is it a dark Jupiter that's in crescent phase? Is it an Earth? And we're going to try to orchestrate how we would do that, because it's so complex to move that star shade to the next target. It's a few days to a week, so we have to kind of be clever in our approach. So we actually spend a lot of time, I can't even tell you how much, arguing over how we're actually going to manage it.
Yeah, I hope you spend a lot of time.
Now, ideally, we'd like to have more than one star shade up there. We have the same telescope, and the star shades are all constantly moving around, and we will, focus on one object at a time.
Now, your excitement is infectious, but we should note this hasn't been approved yet, right? This is.
Oh, well, it hasn't been. Sorry.
I mean, the two things that we talked about, TESS and
right.
Webb telescope, those are in the pipeline.
Those are in the plan, right? Yeah, this has not been approved yet. I thought you said proved, because I was going to tell you how it has been proved.
I'm not from NASA. I'm just a regular
guy. It's really
guy.
cool. Well, I just want to explain. I want to tell you two things with how it's proved, because it's related. But before I get to that, I just want to explain why it's a special shape. And it relates to light being a wave as well as a particle. But light actually is a wave. And if you have a circular screen in space, which would be easier to make, and you're blocking out a point of light, you won't see a point when you take a picture with the telescope. What you'll see is a series of rings, concentric rings. And our analogy is it's like dropping a pebble in a pond when you'll get ripples. And those ripples, especially that first one, as it moves out, that first ripple is so bright, it's actually 100,000 times brighter than the planet you're looking for. So those ripples would kill the whole project. So what the star shade is, it's a very special shape computed mathematically, which in effect pushes all the ripples to the outside. And it would be like dropping a pebble in a pond, when that pond surface would then be so perfectly smooth to 1 part in 10 billion, to 10 decimal places, so smooth. But all away from that smooth area, it's crazy, crazy wavy. And that's what the star shade, we want to do with it. So I just want to mention briefly how we prove it, because we can't demonstrate things at tens of thousands of kilometers. It would be like doing the real thing. We demonstrate that the math works on a smaller scale. In the lab at Princeton, they have a 0.1% star shade. It's about this big. And it's over, maybe the size of some part of this room. And they've demonstrated they can reach the 1 part to 10 in 10 billion level at some, we call it a monochromatic wavelength. And it's being tested actually as we speak. There's a group at Northrop Grumman who are out in the Nevada desert. And they have a 1% star shade. It's about this big. And they have to go 3 kilometers apart. And what they're doing is they have like a fake sun and a fake planet, and they're trying to see if they can see that. So in testing that the math works on a scale that's more achievable, it happens. And then we also demonstrate that the petal can be manufactured. It has to be very precisely shaped and made. And that's what this petal, one thing that it was used for. So I think we can start the second video now.
What's this made of?
This is made of special carbon fiber material. It has to be light because it's so expensive to launch mass into space. Okay, so here you're seeing a test in the lab at Northrop Grumman of petals that are now unfurling from their stowed position. These are just passively unfurling. It's almost a real-time video. There's 4 petals. This is one of those petals, actually. This one here is one of those in there.
This is a mock-up, right? Or is it actual? This is the actual one.
This is the actual thing in here, and these petals are unfurling. Now, this truss in the center, it's left over from figuring out how to build large radio deployables for space, big, huge things that are listening in. And what this is showing you, oh, by the way, I'm always asked, why are there people here? But it's showing you the truss expanding, just like you may have remembered from the animation. And those petals are snapping into place. They're finishing unfurling and snapping into place. And the goal of this demonstration sequence was to show that doing this 25 or more times, those petals would lock into the exact same position to within millimeters. It's demonstrating that the precision actually can happen.
And you wouldn't need those guys running around in space really fast.
Right. Well, the automatic deployment is a separate
Right.
test. But
Well, what do you think? Should we go for this project here?
But before we finish on this topic, I just want you to know it's sponsored by NASA, and a lot of people in all over the country actually have been making efforts to make this thing become physically possible.
So explain to me why that shape. I mean, it's a flowered shape. It's a cylinder, but it's got points on it. I mean, the light. Just explain that again to me.
Okay, I will. Okay, so light can act like a wave, and it can, when it goes around objects, it interferes and weird patterns emerge. And so
So basically, the edges, the fact that it's got
exactly.
a rough edge means that
the fact that it has any edge means that just like waves in water, when they have to go around an edge, it's a problem. And the analogy we use, it's like dropping a pebble in a pond. That would be like the light coming and hitting that star shade. It starts to create ripples in the light.
So it sort of moves through it like a comb on the end.
Kind of, yeah.
Yeah, okay, great.
And it ends up creating this pattern that interferes with searching for planets. We need a very dark. You want to be able to take a picture and not have it messed up by extra light.
And with the star shade, you'll be able to see the planets lit, right? Because
Right. Well, the planets are just like our own Earth. The beautiful images we see from Apollo. It's because they're lit by their star. It's starlight reflecting off the planet.
So your spectroscopy data will be better?
Well, it's essential because the star is so bright that we can. It's like, at least for here in New York, you get snow. I think it's been a snowy winter for you too. Up in Boston, it was a lot of snow. You take a picture in the snow just like the dynamic range, the contrast. It's impossible to take a picture of a person because that snow is just so bright. It just dominates. And that's what the star is like. It just dominates any picture you want to take with the telescope. That it's impossible to see a planet in that glare. You actually have to get rid of the starlight to see the planet directly. And I should add, there's many ways to do this. You can block out light inside of the telescope. There's many ways. But the star shade, it's the one I personally think is the best way to approach the problem in the short term.
Let's take a look again at Earth and some of the conditions for life on Earth, which might simulate some of the extreme conditions that we would encounter, assuming we could see some of these planets using the star shade. What are the candidates on our own planet, Dimitar, that might be a good place to look for conditions for life that are very, very different from what we understand here on this stage?
Well, the whole question about the origins of life, that transition, is when it applied to our own origins and life on Earth is a historical question. So we cannot be completely sure that we can reconstruct the history of what exactly happened in the very deep history of Earth. But in a certain sense, what we are trying to understand is the more general question, and that's where your question is leading to. Are there environments in which we can understand that transition and those possibilities better than what is, in a sense, lost in the old history of our planet? And there are many places like that where you have both access to UV light from the sun or a lot of light from the sun, but also the very complex chemistry that comes with hydrothermal vents in places like Yellowstone, in some regions in not the very deep ocean, but near the surface. And this is an example of a deep ocean vents, but there is examples of something which is more near the surface. And that's exactly conditions which allow you to both concentrate the lipids, which form the vesicles that Jack is making in the lab, as well as some of the chemicals that are necessary to synthesize the building blocks of RNA and RNA-like molecules. And they come together in those cycles of drying and wetting, which we assume are very common on rocky planets. We've seen them on Mars, in the geological record of Mars. and suddenly they occur on the Earth. So those kind of environments give you a sense of what we are looking for that transition to occur, and microbial life, which then we can search for with remote sensing.
So that first image was vents in the ocean.
Right.
I saw the little crabs there. Are there DNA in those little crabs? I mean, obviously there must be.
Sure, yeah.
Everybody.
All life on Earth has.
And it's like 100, but it's like 800 degrees near those vents, right?
But not where the crabs are now.
So the crabs are
Or-
just,
yeah,
they've
they're-
backed away a little
right.
bit. Yeah. But it's also, there's a lot of very, not traditionally life-sustaining chemicals coming out of those vents that
Well, but they are a good source of energy because there are chemicals coming out, and then when they react with the oxygen in the seawater, right, you can really get a lot of energy out of them.
So the second image might be actually more interesting because it's, and that's like a salt flat. That's like the Dead Sea, something like that. What were we looking at there in the second image?
The Yellowstone.
That's Yellowstone.
That's Yellowstone. Okay, so that's right near Old Faithful. So that's the minerals coming out of the
You
water,
have
the
freshwater
geothermal vents.
environments. You have hot water coming out, getting, moving into cold water. So you have very fast temperature cycles. You have all the things that you'd want physically to make a good environment.
Willow asks, which relates to this, to communicate with aliens, should we first study how to communicate with extremophiles? Now, I don't know what her definition of extremophiles is, but do we find in these extreme environments any sense that these could be alien life forms?
No, there's no reason. I mean, it just shows how adaptable life is. And so I think, a lot of planets might be able to support the origin of life when they're young, but then as the planet changes with time and life explores more environments, the planets will be more heavily colonized.
Are these environments extreme in the sense that the adaptation took place from life conditions that are more like our own and they just sort of found their way there? Or how do we know that these extreme conditions actually describe the early times on the Earth and represent closer to the transition?
So, there are organisms that can live continuously at, say, 113 degrees centigrade, right? It's a tremendous adaptation. I don't think anything could get started that way because the molecules we're talking about, like RNA, are pretty delicate. So you'd want them to be in a pretty clement environment, at least most of the time. And so only when they've had the chance to evolve a lot of protective machinery that life could move into environments that are, say, hot all the time, or cold all the time, or salty all the time.
So the extremes might not be so useful to us.
I don't think they're telling us anything about how life got started, but they do show that, once life does get started, it can really spread everywhere on a planet.
Well,
So if you're looking, what we're looking for when we're looking at spectra of exoplanets is we want to see, we're only going to see the effects at a kind of late time when life has had a chance to change the planet.
I wonder if there's a way to gather all the exoplanets that you've discovered and all of the possible sort of billion pieces of real estate that could actually support life and think of them as a solar system like our own. Any idea what that would look like? Aaron, do you think you could concoct something like that for us so we could actually see? Yeah, okay, there we go.
That
There
looks
we
like
go.
transits.
All right, look at all those transits.
That's animation, a very cleverly and beautifully made animation of the aggregate of all the planets and planetary candidates discovered so far, identified so far by the Kepler space mission. And you see them all here around a single star, but they, of course, the majority of them around their own host stars. And it gives you a sense of what we have accomplished in the search for exoplanets in the past 5 years. Most of these come from Kepler, so this is the past 5 years since Kepler was there. It's beautiful, but also it's a cautionary tale. And the cautionary part to that, you'll see in a minute, is the fact that our techniques are still wanting in the ability to detect planets which are far away from their stars, similar to our solar system. And the big question of how unique or common our own solar system is out in the galaxy remains open. We don't have the evidence to answer that question yet, because most of the planets that we've discovered so far within the orbit of the Earth and even within the orbit of Mercury, which is the big circle that you see at the moment on the screen.
So we have our work cut out for us. And think of us as all on this Earth, a very familiar place, on the edge of a huge sea that is unknown, that of course is space. And I'll leave you with a poem from Wendell Berry that describes our relationship with the cosmos in a way that's very familiar. The farmer and the sea. The sea, always arriving, hissing in pebbles, is breaking its edge where the landsman squats on his rock. The dark of the earth is familiar to him, close mystery of his source and end, always flowering in the light and always fading. But the dark of the sea is perfect and strange, the absence of any place, immensity on the loose. Still, he sees it is another keeper of the land, caretaker shaking the earth, breaking it, clicking the pieces, but somewhere holding deep fields yet to rise, shedding its riches on them silently as snow, keeper and maker of places wholly dark. And in him, something dark applauds. Thank you very much, ladies and gentlemen. Thanks to this great panel.